Good afternoon and welcome back to the Calculus Reading Group for our 12th and final presentation this spring. I'm pleased to introduce Torsten Schlack. Torsten spent a number of years at the University of Freiburg, where he obtained his PhD working on theoretical physics and later did a postdoc at the University of Toronto. 2 years ago, we had the pleasure of hosting Torsten when he had just started at Element AI and begun to work on a new library called Hasktorch. Today, I'm pleased to welcome him back to NELA to discuss his recent progress on gradual typing. So the world we live in is getting more and more complex every day, and this is no more apparent than in software engineering. Many look at this complexity and kind of accept this as the natural state of the world. I admire Torsten because he's looked deeply into complex systems and seen how to decompose and reconstruct them in a much simpler way. And if we are to build more reliable, interconnected, and functional systems, I believe that we must look to Torsten's example. Please welcome Torsten Schlack.
Thank you so much. This was a great introduction. Very great. All right, so my name is Torsten. And I'm going to talk about a personal project I've been working on. So the Hasktorch project is something I've been driving mostly in evenings and on weekends. So there's basically I'm doing this with a few friends, over the internet, on Github. This is how this is going. But before I start, let me first thank Brandon for the invitation and for giving me the opportunity to share with you the results of this work. Today I'm going to talk about a new gradually typed API for Hasktorch. And Hasktorch is a library for functional programming for neural networks and tensor computation in a language called Haskell. How do I switch slides? There we go. Okay. So Hasktorch is developed in collaboration with a number of developers for a couple of years now, a bit longer. But my involvement dates back, I think, 2 years. The goal is to bring capabilities of PyTorch, which I think most people here are familiar with. If not, tell me immediately, to the Haskell programming language. So we are building this on top of the C++ core of PyTorch, which is called libtorch. And that makes it relatively easy to bring the core capabilities of PyTorch, which are GPU support and support for automatic differentiation, to the Haskell programming language. And maybe at this point you will ask, why would anyone want to do this? The whole ecosystem of machine learning is in Python. Countless developer hours went already into it. And that is where most people are most productive. And also on top of this, people just seem to like Python. I think that's awesome. And I would say, yes, right now as a researcher, staying with the Python ecosystem is likely the right thing to do. However, one has to keep in mind that the tools we use and we're used to using influence the directions we take when we program, but also in research. And there are some questions that we don't even think to ask, but because our tools make us start from a point where we are limited without being aware of it. So the quote sort of illustrates this. When we start with different tools and a different programming language, or even programming paradigm, such as this is in Haskell, and then we have a different view maybe, and different starting point, and from which we then explore the problems we're working on. And that can open up new possibilities and give rise to new novel ideas. So I feel at this point, I need to say a little bit about the Haskell programming language. Haskell is not that well known in the machine learning community, but it is indeed widely used for programming language research. So it's actually in Haskell where new ideas for programming languages are oftentimes incepted, and then later they find their way into mainstream languages like Python, C++, Rust, Swift, and so on. So just to give you an example, pattern matching was recently introduced to Python, right? And pattern matching has been in Haskell since, I guess, version 1.0, which is over 20, 30 years ago, right? It took a long time for this to be accepted into the Python language standard. Hello?
Yes, we can hear you.
Okay, I continue then. And Haskell is a typed programming language. It models relationships in our data using a type system. So as a person who uses Python, perhaps you think of types as being quite, well, clunky, verbose, more like a pain, because they tend to be one in languages like, well, I have to say like Java or C++. And therefore you feel maybe that they get just in the way, right? So like also like in Python, they seem to be more or less bolted on, right? They started as mere annotations, then they became sort of like documentation standard. And nowadays you can even use tools like MyPy, or I think Microsoft also has their own type checker that help you checking your Python code without running it. And IDEs help you too, right? So like PyCharm and Visual Studio Code, they can make sense out of these type annotations and then tell you, like, put a squiggly line under things they think don't match. But actually, like, it doesn't have to be that way, right? So like types can be a very good asset for you to be productive. And in fact, in Haskell, in part thanks to programming language research that has been going on, it has become possible to make types very expressive without being too verbose. And rather than getting into the way, they help you to get a correct implementation. And this actually can be done iteratively. So there is a concept called hole-driven development, where you start with the incomplete function implementation. You just give the signature, and then you sort of enter a dialogue with the compiler that helps you arrive step by step at a correct implementation of the function. And we'll see more of that later. And then the third kind of aspect we have to be aware of is the aspect of functional programming. And that's a programming language paradigm where function composition is a core building block for writing programs, right? So like in Haskell, not only are functions first-class citizens, they're also sort of like the essence of many things you do. And you have functions that take functions as arguments, like higher order functions. And this becomes very natural. And the syntax and the language is engineered to make this very, very nice. It turns out that there are actually deep connections between function composition, functional programming, and building neural networks. So in fact, if you're interested in diving deeper into this, there's a great blog post, already posted a few years ago, by Chris Olah. You can just Google for it, about neural network types and functional programming. And I can recommend this a lot. Okay, so what do people do with Hasktorch? What are the things that are happening? So there are a number of different directions that people explore using Hasktorch. One area that seems to be getting more popular for a lot of researchers around the world is the area of program synthesis. So program synthesis is sort of about automatically generating or completing programs using AI, where AI can be ranging from like, I don't know, like neural networks, but also more classical symbolic reasoning techniques. And this is a topic I'm personally very interested in. And I also spend a lot of time in my work at that. So like I work at, for instance, text to SQL translation, where you try to generate SQL code based on an input natural language utterance. And actually here on the top right, you can see a snippet from Chiara Graustra's approach to program synthesis. And she had a NeurIS paper recently on that last year. So her paper was called Type-Driven Neural Programming by Example. And there you actually give input-output examples and a type signature of your function, and the system tries to synthesize the body of the function. And one reason people are finding program synthesis in Haskell interesting is that Haskell's type system can be used to implement compilers in a very robust way. And you can combine this ability to write compilers and even implement new languages with program synthesis capabilities right built in. And that has been done with tools like Haskell. One other thing is, so in the bottom, you can actually see a recording of a talk I gave last summer. And there I tried to show that when a compiler, so the Haskell compiler, knows about your neural networks and tensors you're using and their properties, it can give you hints. And this is almost sort of like a next generation way of interacting with the neural network, where the compiler can tell you, oh, hey, you have a shape error here, and here's something you need to fill in, and here's what I have in scope for you that could fill that hole. So sort of like what I mentioned before, you enter in a dialogue with the compiler that just like constantly monitors what you're doing, and then helps you when you're stuck or when you did a mistake, points it out to you. And you can all do that before even running your problem, right? So like you don't have to run your executable in order to figure out that there is an exception waiting for you. You get these kind of integrations already today with the Haskell language server integration to, let's say, Visual Studio Code, but also works with other editors like VI or Emacs or others. And I will show you some of that in a bit. But before that, let me just go mention briefly some other things that are going on with Hasktorch right now. So Junji Hashimoto is exploring new features, and he's very good at updating also the libtorch bindings whenever a new version of PyTorch comes out. So I think it took him like a couple of days to ready a PR that updates from 1.7 to 1.8 when it came out. And this is because most of the marshalling code in Hasktorch is generated automatically. So you basically hit a button and then you get all the glue code that you need to talk to the libtorch library generated for you. And then it's just a matter of like sorting out some signature changes in the downstream code. But everything else is taken care of. And it's very, very efficient. I'm currently exploring implementation of transformers in Hasktorch using Gradual typed tensors and neural networks. So I will talk about this in a bit. And I will show you that. And this summer, we will collaborate with Google Summer of Code students to improve this API further. And besides that, we're also working on improving the documentation. So Matt Whitman is working on a series of tutorials for beginners and people who are already familiar with PyTorch. And Austin is exploring Hasktorch-powered apps. So basically, this brings us a step closer to deployment of models and services. So this is a bit of an overview of what's going on with Hasktorch right now. So are there any questions at this point or anything you wanted to point out more detail?
Yeah, just kind of a high level, maybe a question. You talked a little bit about compositionality and how you want these things to compose and be well typed. And you mentioned a little bit about program synthesis, and that you're trying to fill in holes in types, missing types, and things like this. So you're saying, if I understand correctly, that you see a way to combine, or you'd like a common language to do this in, at least, and maybe there's a way to combine these kind of classical type-driven program synthesis with a more language model based approach, where you're kind of looking at statistical correlations between programming language primitives. Is that correct?
Yeah, so I only mentioned that in passing, right? So like this is not what this talk is supposed to be about, but I can talk about this a bit. So what I mean is that you may want to okay. So let me take back. So like maybe you're familiar with proof assistance. So like I don't know, ACTA or COP or Lean or systems like that, right? And there is a mode of these proof assistants called the tactics mode. And what they allow you to do is like you can basically, I mean, the essence is you want to prove something, right? Some theorem, some statement. And of course, you have sort of axioms there and like other theorems that you can reference. But this tactics-driven approach to proof synthesis, what allows you to do is sort of like gives you the ability to tell the proof assistants how to work iteratively towards the proof, right? So like apply lemma such and such, expand, do stuff, right? And you do that on like sort of semantic level. You tell the system what you want to do, not necessarily exactly how to do that, right? But if you're in such a mode, it's like really like almost like having a dialogue with your system, where you sort of like listen to what the system tells you and then try to react and give it the next instruction, or maybe even go back, right? So it's sometimes it can be more like backtracking search, but in other cases it's sort of developing straightforwardly. And there's a little bit of a connection to this like type or like hole-driven, typed hole-driven development style you have in Haskell, although it's not really working on a semantic level. Well, somewhat with types, if you think of like types of semantic representations of behavior, but like, and they're like tactics like approaches to generate code that are developed at the moment that are actually being integrated into the Haskell language server and then already available from Visual Studio Code. So you can tell the system like, so if you have a data constructor and it's just a sum type and you maybe have 3 constructors of that sum type, you can tell the system just expand, right? And like make me one binding for each of the 3 constructors. And then the bindings, of course, don't have a body, right? So like they're not bound to anything except like a typed hole. And then you look at the first typed hole and you do something else so that you ask the compiler, what is the type of that typed hole? And of course, the compiler can tell you that. And then it tells you what bindings you have in scope. And then you maybe choose one of those, right? Because you think it may be fitting here. And then you have another hole to worry about because these things sort of like when they grow a tree of expressions, right? And you can sort of think of now that this could actually probably become something you could automate, right? Because like on one hand, it's sort of like search. But if you just do blind search, if you're not sensitive to the semantics, not sensitive to what's plausible, given like what the user wants to do with this, I mean, you just end up having like a collection or a long list of possible candidate implementations of that function, right? Because many things typically fit like the type signature of it. But if you could combine that with something that tells you the plausibility of what the system comes up with as a candidate, maybe rank them in order of, in decreasing order of plausibility, given sort of like maybe the names of the variables, maybe the names of the functions that you want to implement, maybe the type signature itself, maybe based on what has already been implemented elsewhere, right? Like if you have a corpus of already written code, you can learn from that, right? If you take all of them into account, then maybe you can actually come up with a ranking of these candidates, which actually like a tactics-driven approach can typically not give you. And then it's up to the user to select the ones that fit most. But maybe with AI, or if you combine that with sort of language model techniques, you can come up with a ranking. And then maybe the first ranking is already the one you want.
That's a very interesting digression, and I didn't mean to kind of derail you there, but thanks for elaborating.
So if you're interested more in that, so it seems like I'm actually like going more down into this right now. If you're interested more in that, we can talk about this as well if you want, but I'm developing something about this also off work at the moment with a friend on Twitch. He is from Montreal. His name is Samuel. He actually is one of the, or has been one of the organizers of the Montreal Lambda meetup. And once a week, or right now, once every 2 weeks, we meet on Sundays on Twitch where we basically develop this together. And we're making good progress there.
Very interesting. Yeah, maybe we'll put that in the show notes the link to your that Twitch stream, and yeah, hopefully get to hear more about that in the future. Thanks.
Okay, anything else? Doesn't seem to be the case. So, so the next thing I've planned was to show you a black screen, because I'm gonna end the presentation and I'm going to switch to this window here, which I will first make larger. And please tell me if the font size isn't good, or if you can even see it, because I'm not sure. Can you see the Visual Studio Code video?
Yes, I can see the contents of the
Okay.
editor, and maybe if you could make it just a little tad bigger. I don't know if that's easy to do or if not a big problem.
Well, it's very easy to. It's just at some point, because, well, I mean, it's okay now. Is it better?
Yeah, looks great.
Okay, so there's a lot of stuff going on. So what I'm going to show you now is how Hasktorch code looks like right now. And then tell you what the heck this gradual typing is about I was talking earlier about. So there are two existing APIs already in Hasktorch. There is an untyped API. And when I say untyped, I mean it's sort of like there's a tensor type, and that type is actually right here in line 54. And that says a tensor is a data constructor around a foreign function pointer into libtorch. So what that means is that you sort of have a box around a pointer that you carry around. And this is sort of also like how it works in Python, but you don't think of it this way. And you don't know what's in that box, sort of. Like, you know, it's pointed to a tensor, and you can use that pointer because other functions take this pointer as an input, and then maybe give you another pointer back, or the same pointer with the mutated content, and so on. But what's not tracked here is how you change the tensor when you apply it to a function. So for instance, if you move the tensor from the CPU to a GPU, right? Or if you changed a long tensor to a float tensor, or if you added a new dimension, like you unsqueezed it, or even you could squeeze it, or you can broadcast it or whatnot, right? So like shaping information is also not tracked here. So this is sort of like all in, I mean, it exists on the value level, like you can write functions that pull that information out, but the compiler, the Haskell compiler here, has no insight into that. It cannot reason about this. And that means that, for instance, like when you write functions, so for instance, here's the function that returns the total number of elements in the input tensor, right? You may know that from PyTorch. Takes two arguments, it takes one argument, the tensor, and returns an integer, which is the number of elements in the tensor. And you can see the implementation of this here, and you can also see the essence of how this works in Hasktorch right here. So like the number of elements function. So like if you haven't seen Haskell code before, so like what I selected now is the function signature. So first comes the function name, numl. Double colon separates the name from the types. The first type is the input type, which in this case is the tensor. Then you have an arrow, which separates arguments from each other. And the last argument in that type signature is actually the output type. So this is a function from tensor to input. And what's in between, which is displayed here in gray, are just doc strings. So that means here the input is the tensor, and the number of elements of that tensor is the output. And the implementation is below. So you define this declaratively. So you give the name of the function, then you bind the input argument to this variable name here, t for tensor, and then you call functions one after the other on that argument. And the $sign sort of like is a quick way to avoid parentheses. So it just means like first comes the t, then we apply this t to this function here, tensor number of elements, then on that we apply actually another function called cast1, which I will not explain now, and then we call something called unsafe perform IO. And so it's like read from right to left in this case here. And this function will just return the number of elements, right? Actually, in this case, it will not have to take into account, well, what it does is like sort of, it asks the libtorch backend, which we refer to here by A10, and using its way to inspect the shape of the tensor to compute the number of elements, right? So like completely rely here on the implementation in libtorch to provide this functionality. And this is actually how many of the functions are implemented, right? Just the size, so like how many dimensions do we have? What's the shape and so on. So like this all is delegated, dispatched to basically libtorch functions. And if we had a way of tracking the shape of the tensor in the type system, we wouldn't actually have to ask libtorch about that shape. We can compute it from the typing information. So I show you now a different way of encoding tensors in Hasktorch, which is based on more fancy typing, if you want. And it's here in line 128 in a different file. And here a tensor is represented again as like a wrapper around something else. In this case, the data structure we saw before, this tensor. But now we are tracking the device, the data type, and the shape of the tensor in the type system. So this tensor actually has type arguments, 3 in total: device, dtype, and shape. And then we have a constructor which is called unsafe make tensor, and it's made in such a way that you can wrap, or like you can take. So it's another box around this dynamic tensor, so the tensor without typing information. And for each one of those, it returns to a type tensor. And this constructor is marked as unsafe here because when you construct it, like it doesn't check really what's in the box, right? So if you say, well, this tensor has this device, this dtype, and this shape, these annotations, they may actually not correspond to the true, or like the runtime shape of that, the runtime device, data type, and shape of that tensor. So that's why this is unsafe, and you actually discouraged from using that thing for obvious reasons, because if you say it's on the CPU but actually lives on the GPU, well, that will create problems further down the line. And this thing also has a number of elements function, which I'll have to find quickly. Yeah, I think it's here. No, it's not here. Ah, it's here.
Torsten, sorry.
Hello?
Yes, so you're showing the type level numl here, the function that returns the number of elements at the type level.
Yeah. So this is how do you do that with types. Sorry, my mouse. There is a way of defining functions on types in Haskell, and this is called a type family. And what you can see is an implementation of the number of elements type family. What it takes as an argument is a type called shape here, which is a list of natural numbers. And this type family has also a return type, which is again a natural number. And it's also defined declaratively, right? So like if you give this thing a list of natural numbers and that list happens to be empty, well, then the base case is that we have one number of elements, right? I'm sorry, the number of elements is 1. Which means like if you have an empty list, then it means that must be a scalar, right? And a scalar is just 1 element. And if you have a list that has more than 1 element, you get well, you can deconstruct that list iteratively, right? First, you take the head of the list from the tail, and then multiply the head, which is a natural number, times the number of elements applied to the tail, right? And that gives you then, when you compute this until you reach the base case, the total number of elements in that tensor. So the problem now is that we have some sort of like strong dichotomy here between untyped and typed. When we have an untyped tensor, what we can do is, and what we can always rely on, is that we can ask the backend, libtorch, what is the runtime shape of that tensor? And if we have a typed tensor, then we sort of are encouraged, or sometimes even forced, to use the types, in this case the shape type, to compute the number of elements, right? Because what you assume is that the typing information that you attach to your tensor are all equivalent or equal to the later runtime properties of that tensor, right? The shape annotation that you have at compile time should match the shape that you actually get when you run your program. So, so when you commit to the typed API here, you're making the assumptions that what the compiler thinks your types are, your shapes are, your devices are, your data types are in fact the runtime shapes, devices, and data types. And there's no middle ground. So you cannot say that, like, I know a little bit about my device, maybe I know that it is sitting on CPU, but I don't know what the data type is until I run the program. And I don't know maybe what the shape will be, because it's computed somehow from some term that only becomes available at runtime. And so you have to either commit to something that's fully checked at compile time, or you have to commit to no checking at all. And yeah?
Torsten, I don't know, is there a way in Haskell to call the type level, the type family implementation here from runtime without doing the type checking? Because I mean, if you have two implementations, does this become a problem? Here you have kind of an inductive a definition of numel, and then the other one, this is computed in a different, there's no code sharing.
Mm-hmm. Yeah, there's no code sharing. So like if you wanted to implement this on the type level, you would have to, I mean, some languages like dependently typed languages allow you to lift term level computations to the type level. And in Haskell, that is also available to some degree using a library called singletons. But in many cases, I mean, I could have done this here, but in many cases, you don't really want to do that. Especially here, it's impossible because we delegate all the value level computation always to the libtorch backend, right? And that's a complete black box. We cannot like introspect how libtorch would compute this and then lift that somehow into a type level computation that's running a Haskell. That's unfortunately not possible. But what we can do is we can, so I mean, these things are relatively simple, right? We just like multiply each element in the list with one as a base case for the empty list. So like these sort of things can be re-implemented at the type level, and the compiler can run these computations when it type checks your code. And that runs actually quite fast. And unless actually your types would depend on the outcome of a tensor computation, you're in a very good place.
Excuse me, Torsten?
I see, yeah, thanks. Yeah, I suppose you're going to show something in the middle, right? I interrupted. You were saying something about there's something in the middle. You don't have to choose this strict.
Yeah.
Lazily.
So with gradual typing, you sort of get to most of both worlds. So like maybe I didn't motivate this well, but like let's suppose like you are a believer in types are here to the rescue and to help you actually to be more productive. And there are good reasons for believing that. I am myself actually commit to this fairly strongly. Then, and you wished you could use these strong types throughout your whole project. Turns out though that, especially with algorithms, the typing can sometimes get in the way of sort of making headway in your implementation, and also they can, I mean, sometimes they guide you towards a better implementation, no question, but like sometimes they're also like sort of, you want to do it first without types, because proving actually, or telling a compiler, or like creating witnesses that some things are in fact true is a struggle sometimes, right? And maybe it's first better to do like an untyped, or a part of an untyped implementation, just to see if what you want to do actually has a chance of success, right? Maybe the algorithm that you're thinking of is completely bonkers and will never really work. But if you committed to a typed implementation, then you would have to do the extra work of proving to the compiler that your types actually check out. Well, in fact, you have to throw away that implementation anyway, because well, your idea was just unsound from the beginning, right? And if you had used something that is like low effort, has less opportunity cost, right? You may have discovered that earlier. And if you actually make something that works, but then you have to sort of like make it more mature and actually sort out the edge cases that you may not be aware of, then it makes sense to sort of gradually increase the degree of typing, and start maybe from an completely untyped version of your algorithm, and then gradually introduce more and more types to a point maybe where it becomes like tedious or even impossible to like add more stronger types, and then you stop. Or you may decide you don't need types at all. But at the moment, sort of like you cannot do that with these two APIs, because one is like untyped, you don't know what the tensor is, what the parameters of the tensor are, and in the other paradigm, you know everything ahead of time, but this sort of like forces you in this narrow space of things that can be expressed, right? Where this information is actually known ahead of time. And what I'm proposing is like, why not do both? Or why not like sort of interpolating between these two extremes?
Yeah, I think that makes sense. I mean, can understand the motivation for migrating kind of less strictly typed code to this style, to have something a little bit more user friendly. But just to go back to the semantics for a second, so you mentioned you'd like to have this property as well as if you're in the middle of this migration process to have some assurance that the if you say that there's a certain shape at compile time, then it should have this this shape at runtime. And just curious if there are any you know, if you want to be conservative and just not provide any information, maybe that's not as helpful, or as you kind of try to make more assumptions, there's some trade-off there that you could make, I suppose, and you know, the user should be able to rely on the information that they're given, that's an accurate reflection of the runtime semantics.
Mm-hmm. I'm not sure. Was there a question somewhere in there?
Okay, so maybe so when you combine two tensors, right, with an operator, mm-hmm. At compile time, is this done kind of eagerly, in that you compute this numl as soon? I know there's some lazy semantics in Haskell, and at runtime you showed the other example of numl, and this is maybe done when the user requests mm-hmm. need the very last possible moment. Mm-hmm. Is there some mismatch there, or it's always a lazy evaluated numl here?
No, so like type level computations of Haskell are eager.
Ah, interesting.
always. Sometimes that can actually pose a problem because what you do when you use these type families, you build up sort of like this tower of type level computation sometimes, right? So like you build this expression tree, and sometimes these can become quite big. And you cannot tell the compiler, defer evaluating this expression, this type level expression tree when you actually need it. The compiler will eagerly try to evaluate the thing and will put this in memory. And sometimes, especially when you have type errors somewhere in there, which the compiler has to report to you, because this is how the thing is built, that could lead to excessive memory use.
Yeah.
So you have to be aware of that when you design this stuff. But yeah, so like type level computations are eager, value level computations, unless they're specially annotated, are lazy. But you can also do strict computations.
Thanks.
Right, so like maybe I can motivate this with one example of an algorithm I looked at, which is beam search. I'm not sure if you've heard of beam search. So beam search is an extension of research. It's used, well, I use it mostly for autoregressive generation from a language model. So what happens there is like you start with an initial state, and let's say you have something that is like, I mean, let's say you have a transformer model and you have an encoder and you have a decoder, and you initialize your decoder after you encode the input to the model. You initialize the decoder with a beginning of sentence or beginning of sequence token, a BOS token. So what happens then is that the model will build a representation for this BOS token, which at the end, when there's a language head on top, will give you a distribution over all possible tokens that are in the vocabulary that could be the beginning of the sequence. So like, for instance, if you have a language model that translates English to French, the first token that your model produces will just be the beginning of the French sentence that it tries to write, right? And so then you have the distribution, and research. What you do is like you just take the top one result there, right? The one with the highest probability among all of these possibilities. And what we do with beam search, you say, okay, I look at the top k, and I just take, in the first step, I just take all of them, top k, and I have sort of like k items or hypotheses in the beam that I keep around. And at the next iteration of this algorithm, when you try to predict the next token in that sequence, you feed all these k alternatives to the model again, right? And for each of them, you get again maybe 50,000 different alternatives, right? So now you have k times 50,000 possible 2 token long hypotheses. But since your beam size is limited to k, you have to narrow this down to total k, right? So how do you do that? Well, you keep around a total score for each of these hypotheses, and you just sort all of these k times 40,000 things by their score. You only then take the first k, right? So this is how you do this with beam search. So if you try to do that with untyped tensors, this has been done plenty of times, you can write down this algorithm, and after a bit of trial and error, it will work. But if you try this in a typed fashion, you have a bit of a problem there. First of all, beam search, or like the number of hypotheses in the beam, the beam size or number of beams, is typically a hyperparameter, right? That means like you will have a configuration file that says beam size is 5, or beam size is 1, or beam size is 100, I don't know. And you don't want to recompile your program whenever you want to change the beam size, nor do you want to recompile your program when you change the batch size. Because if you had introduced the beam size as a type, then that would require recompilation of your program, or at least the module in which that type occurs. So if you compile incrementally, and so wouldn't it be nice if you could just say, well, for that dimension, which is the number of hypotheses in your beam, please use an untyped value, right? So like represent that dimension on the term level and not on a type level. Because if you represent it as on a type level, your compiler would need to know it ahead of time, right? In order to reason about it and check everything. And well, and it becomes worse because like you start producing more and more tokens, and at some point one of these hypotheses will end because the model predicts now the end of sequence token. So that means, like, let's say one of these hypotheses is now complete. You don't want to continue that completed hypothesis anymore. You want to put it in some bucket that says finished, right? And you don't want to keep it around or add additional tokens at its tail. That would be just wasted effort. So now you have not a beam size of k anymore. You have a beam size of k minus 1 because one of the hypotheses is finished. So like the number of hypotheses in the beam is also sometimes something that changes at runtime, right? So like you could come up with actually a type computation that models that and that does it correctly, right? So you can reason about like adding or removing hypotheses from a tensor on the type level, but maybe when you implement that beam search, you don't want to think about that too hard, right? You don't just want to implement the first draft of that, beam search algorithm, and then when you think that algorithm is sound and you're happy with the API around it, maybe you want to make sure that the thing actually works correctly by adding this additional typing information. And that again can gradual types help, because well, you could say the beam size is something that you don't want to touch at the type level. This is something that's always handled at the value level. And then of course all hands are off with regards to its soundness, and there may be a runtime exception if you don't handle it correctly. But at the same time, the compiler could still reason about all the other dimensions of that tensor, right? So for instance, if you look at these 40,000 different tokens, the vocabulary size is typically something that is known well ahead of time, because you will have a tokenizer that is trained with a certain number of tokens. And unless you want to add tokens to the vocabulary, which is something you may want to do, but typically this happens rarely, this number is pretty fixed, right? So maybe that makes sense to use types for modeling this dimension.
Right. Yeah, I think what you're saying makes a lot of sense, and it sounds like what you're working towards, if I understand correctly, is that you want to separate, what to do from how to do it. So if you completely specify, the shape of all the intermediate steps, maybe this is kind of less declarative and more, here is how you execute the computation. Because I know one topic that we've touched on in previous discussions here is, well, you have a tensor and you can do the contraction in multiple orders, and this ordering might have different intermediate shapes inside of, and so if you let that kind of intermediate the contraction ordering be more flexible, determined at runtime based on the shape of your data, then maybe that's a good thing. And yeah, so you're saying it not just for migrating from a loosely typed to a more strictly typed API, but also this is something that's desirable from an implementation level.
Yeah, you can like if you had to decide between typed and untyped, right? And there were only these two possibilities. If you do untyped, I mean, it can be done, right? Because languages are Turing complete and you can model whatever you want typically, right? And you will find an expression of the correct algorithm probably. And if you do it typed, you may also arrive at that. But for this example that I just gave you before, beam search, that algorithm, like you will go through some mind-boggling exercises in order to set this up correctly, right? And maybe it's just not worth it.
Yeah, I could see that. I mean, you know, you want this type system to be able to give you quickly, you know, you could implement, I suppose, the entire thing at the type level, but
yeah,
it really is not so beneficial if it just takes as long to evaluate it. So is that something that you feel you've made the right trade-off here? I mean, you mentioned a little bit about the memory efficiency of evaluating these terms and depending on your
so like
representation.
just to give you an impression of that. So like what I've done is I've implemented the T5 model, and now actually also I've implemented several others. So like we have here Bart, we have Bird, we have Roberta, we have T5. So these are like big transformer models, right? So what I've done here with the help of a friend on Twitch is I've implemented these models using this gradually typed approach. And basically, we define just a bunch of forward functions, right? So like we're following sort of like the high-level paradigms that PyTorch introduced. So like applying a model or like a module to others always involves the forward function. So like we call our thing forward here too. And then an algorithm proceeds by just gluing together, composing these forward functions. And this looks funky now to you, and I haven't explained the syntax necessarily well enough to make sense of this, but believe me, when what happens here, you define a function, a forward function in terms of other forward functions. I think this part may be clear. And what the compiler can do is like it can reason about how the tensor shapes mutate at the type level, subject to this composition, right? So it can tell you like if I take this input tensor with this shape, and if that input shape actually happens to fit into this computation because it's compatible with it, then the output type of that, or the output shape of the tensor will be such and such, right? So like this is handled by the compiler entirely, and it can check all of this at compile time before you even run the program. So what I've done here is you can wire up a whole T5, right? And here's a little bit of a test input. So like I just gave it like raw integers where each integer corresponds to one token ID, right? So this is token number 13,959. And this list is the first sequence in the batch, and this list is the second sequence of the batch. So these are like the inputs to the model, and these are the decoder inputs. So like you would use that when you want to train your model, you would give it both inputs and labels, right? And the decoder inputs are basically the labels. And you give, there's this public function here, make T5 input, which takes this value level list, right? So like these are just values, and this is like a doubly nested list here. And you give it two type applications here. So like an unnamed dimension and a sized, which is sized at the moment. So like a batch size 2, and the sequence length is 51. So this is basically meant to like fit in a box that's 2 by 51. And for the decoder outputs, it's 2 by 42. So it just shows numbers so that both of these sequences would be fitting inside these boxes. And then you can see that there's a weird type annotation here, test T5 input, : IO of underscore. So underscore is special. What it means is this is a typed hole, and I mentioned that I think before. So typed hole is something that the compiler is prompted to infer for you what the type is and what fits in there. So this make T5 input function will produce, based on these two type applications that give you the dimensions of the output tensor, will produce, again, an output shape, and the compiler here can just fill it in for you, basically. And here it says, well, of course, because you told me this is 2 times 51. So there's no magic here, basically. But this wildcard is sort of like a way of saving a bit of space, right? Because we have type inference, why not make use of it? And the same here for the decoder input. And then if you wire this up, so like we have here a model that is initialized from a T5 small checkpoint. we can use the forward function of that model, which is the whole T5. And I think T5 small, I think, has maybe 6 layers, both in the encoder and the decoder. So 12 transformer layers. Actually, it's 18 transformer layers because in the decoder you have also the cross attention. And so this is not a super small model, but also not very large, right? And the compiler knows here, because I told it what T5 small with language model is, that this model has these dimensions. So I'm not exactly sure what they stand for, but I think these are like the dimensions of the linear layers, or like the fully connected layers that are inside that transformer model. So don't ask me which one corresponds to which one. I think this is the number of heads. This is the embedding dimension. I think this is yet another embedding dimension. This is the vocabulary dimension, so with 30,128 tokens, and so on and so forth. So the forward function now takes the inputs, these 2 inputs I had above, and we know their shapes, 2 times 51 and 2 times 42. We apply the forward function to both the model and the inputs, and we get an output. And what is the shape of that output? It is, well, 2 times 43 times 30,128. So this is something that the compiler just computed for me. And if I commented this quickly, so now nothing works anymore, right? Because, well, I just broke my code. But if I comment this again, uncomment this, I mean, then this reloads back, and this was instantaneous, right? So there was almost no time. And I can prove you that this is running in real time. I say here 57. Oh, I said 75, sorry. And without delay, I get here 75. Right? So like, this is really, really fast. And if I increase now the model, if I don't say, I don't want a T5 small, I want a T5, what is it? 11 billion parameters. Okay, 11 billion parameters. So this model now has, I believe, 24 layers in both the encoder and the decoder. And you know, like you have, basically what that means is like you have forward function on top of forward function on top of forward functions, like 24 times now the transformer blocks that you have in each of these sandwich layers, which individually also have forward functions in them, right? And instantaneously, the model was able to compute all of that type information and gave me now, again, this output shape of the tensor that comes out of this. But it computed all these types, all the intermediate types, and told me what the output type of this whole stack of computations is immediately. And I get this in the Visual Code UI served to me immediately. And if I made a mistake, right? So if I took here, I don't know, backslash 3, then, well, loading. I think it would actually give me a typing error. I'm not sure why it doesn't give me one now. I think because it's like still trying to make sense out of this. Yeah. So just to give you an impression of how quick that can run. Unfortunately, you cannot execute this because T5 with 11 billion parameters, I think, is a 46 gigabyte model at the moment. And that doesn't fit even in my CPU memory. So I don't have a model that can run this, or a computer that can run this model. But yeah, just to give you an impression of how fast this is. So like model size typically has almost no impact. But this is only because I optimized the type computations a little bit to make this better. It took some effort, but it's possible.
Yeah, interesting. So I guess this depends. I don't know if you're using a Haskell library to do this where you encode the dimensions, or is this completely implemented? You showed the example for multiplication. Usually that would be like the multiplication operator that's implemented by another library, or you did that as well?
I implemented all of this. So this took actually quite some time, but just to show you one tiny element of it. So here's the linear forward function. Mm-hmm. Where is it? Here. Forward is defined as linear without bias. And linear without bias takes two tensors, one for weights, one for inputs, and delivers you an output. And you can see here, so we take a tensor that has, so it requires gradients is basically just a type level Boolean that says, do we have gradients for this tensor or not? Or do we want gradients for that tensor or not?
Yeah.
And we have layout, is it sparse, is it dense? What device that is on, what's the data type, what's the shape? So this is all now this gradual type API, right?
I see.
And then the output type is a tensor again. So what is now the required gradient? Well, we have this little operator here, which says, look into requires gradient prime of that input tensor. If any of those requires a gradient, well, the output also requires a gradient.
Mm-hmm.
Then we have layout, and we have this other little brackety plus operator here. So this thing unifies A and B. So if A is layout and B is a layout, then this is sort of like a kind level monoid. What it does is sort of, it inspects, are these two actually represented at a type level, sorry, on a kind level. So do we know the layout or do we not know the layout? If for one of those we do not know the layout, we will not know the layout for the result of this computation. So all bets are off. Uh-huh. But if we know the layout for both of them and they do agree, then we let this pass. If we do not know the layout for, if we do know the layout, but for one it's dense and for the other one it's sparse, then this will crash at runtime, so we forbid it on the type level. So I can show you this below. So here's weight and input, right? And here's layout. If you say one is sparse, then this raises a type error. And it says, the supplied tensors must have the same memory layout, but different layouts were found, sparse and dense, bam. Mm-hmm. And this is because I implemented a type family for this bracket plus operator that looks at the layouts, and if it finds different layouts, it emits a type error. And you can express these sort of computations in Haskell code itself. You can actually control and you can manipulate how the compiler reacts to type errors by writing extra code. So like you have actually a window into how the compiler works internally. Mm-hmm. And just to give you a flavor of like how this gradual typing works with the sizes of the tensor. So if I say the input has size 1, but if I say unchecked size, so now I've not given the compiler any information about the size of the first dimension of that input shape of the input. Then what is the output of this? Well, it's not sure what happens. Sorry about this.
No, I think.
Right, so maybe I should write it like this.
Clear.
Found the wildcard, and what does it say? It's standing for output size 2. Interesting. This should actually not. Oh, right. Did I discover a mistake here? Oh no, it's because, haha, if you have a linear layer and you apply it to an input, then the only thing that matters is the output size of your weight. Mm-hmm. And therefore, we cannot say much here. But I think if I said this is size 1 and this is unchecked size, so now the weight, the output dimension of the weight is unchecked, then that means that the output of that function is also unchecked, right? So like the compiler wants the unchecked size, but I've annotated this function with size 2, and therefore I get a type error.
Yeah. Could you, if you're writing a combinator for 2 tensors and one is unchecked or one is you don't know anything about the dimension, but you know the other, could you infer either a lower bound on the shape, or you could have certain dimensions, right? So some you might not know, but some you do know. It seems like depending on the operator, you might be able to keep the dimensions that you know and then throw.
Yeah. So I think this is a good point, and I think this is a decision that you have to make on an operator basis. Mm-hmm. So there may be operations that where it's clear what to do. There are others where it's less clear. So the philosophy I follow here is typically one that when you have to make sure that dimensions line up in a certain way, right? So for instance, if you have a convolution operator and there's just a very clear constraint between all the input shapes so that this thing works, it's necessary to, because like you want, I mean, when you have typing information, you want that the typing information give you safety, right? Mm-hmm. And you don't want to be thinking that like, when you don't give enough typing information, you're still in a safe place. So the decision that I've made typically is that once one of the elements to the constraint, like one of the input shapes has insufficient information because it's just unchecked, or declared as unchecked, then the output of that operation will also be completely unchecked, or at least partially unchecked. And that's just because, like, look, you've given me not crucial information here, therefore I cannot really tell you if what you're trying to do makes sense. Hence, I will declare this as unchecked, meaning it's potentially unsafe and unsound to do. But I won't like, I mean, I don't want to raise an error here, right? Because well, what you're doing may just well be all right. It's just that the compiler cannot reason about it. Therefore, I have to declare this as unchecked. That's it. Yeah, but you're totally right. And like, I mean, there are also like, there are many operations that destroy typing information actually. So like if you, like you can see here, we have always this monoidal thing, right? You can think of each of these dimensions or typing annotations as some sort of like thing that is wrapped in a maybe. If it's a nothing, that means unchecked. If it's just something, that means checked. And the monoid instance for maybe is such that like if you have one nothing, then the result is nothing. If you have two justs, only then you get a just back, right? And here's the same thing. So you have, if you have one unchecked thing, then the result is always unchecked. If you have both checked, then the result will also be checked.
Yeah, interesting. It might help to kind of write down the typing rules. I don't know.
Yeah, let me actually bring them up because they are written down in this thing. So for instance, here for layout, so we have here this type family unify. So again, a type family is just a type level function. So this is implemented as a function on the type level. If you want to unify two layouts, one is unchecked, and then it doesn't matter what the other one is, the result will be unchecked. And then we have here the flipped one. If both are checked, so we know the layout on the type level, then, but if the layout type are different, if the types are different, then we produce a type error. But only if they're the same, then we'll let this pass.
Yeah, interesting. That looks very succinct. It's kind of like the way you would think about it. It's written in a very readable syntax here. It's interesting. So here you're keeping track of the individual dimensions in a kind of a rank 1, 10, or just a list of of shapes. Do you think you could or you'd have a need to track actually materialize the tensor at the type level, or is that something that you want to index a tensor by another tensor? I don't know if that's something people do.
Yeah, that's tricky, right? So indexing a tensor with another tensor, I don't think this can be done on the type level.
Yeah.
But this is where this API shines, right? So you can still do that, although I haven't implemented it yet. But you can still do that, and without sort of like interfering with where you actually want to use stronger types that are not, where the result does not depend on the runtime values of things you're working with.
Yeah. It seems like, you know, there's some operators that might have you could just do at runtime, like well, for convolutional arithmetic, I know you probably implemented those rules where you have like in images, and you have to do some addition, multiplication, division to get the resulting size of your kernel convolved by your image convolved by the kernel. Yeah, it seems like there's a large possibility space, and like you say, you have to kind of focus on the use cases that people have and make it performant enough to run with low latency.
Yeah. So the good news is like all of this type level stuff, right? Like this unification stuff, even like this stuff here, right? Calculating with the output shape of this tensor that goes through a 24 layer transformer. That is all erased from the runtime, right? So like all these computations are going on in the compiler, and nothing of that will impact the runtime. Actually, the runtime is as fast or as slow as libtorch, because everything goes just straight into libtorch. All the tensor math, everything is handled by libtorch. The numerics is exactly what you would expect from PyTorch or libtorch. And actually, this thing here, test forward T5 small, makes sure of that. Because what we're doing here is loading a T5 small model, or T5 3 billion if I had a computer for it, and then we're giving it an input. And here are actually the logits we expect as the output of that computation. And these numbers I've taken from the Hugging Face implementation of that thing. And I'm making sure here that they match to 10 to the power of -4. And this is only possible because eventually at the end of the day, they just do the same math. It's just it's different from the end. One is in Python, the other one is in Haskell here. But they do the same computation.
Huh, yeah, that kind of magic numbers there from the Hugging Face implementation. So you've re-implemented like all the Hugging Face tokenizers and things like that?
Yeah, so the Hugging Face tokenizers wasn't re-implemented. Again, the Hugging Face implemented this thing in Rust.
Yeah.
And what we've done is we just made a Haskell binding to the Rust libraries through a C layer, actually. I cannot show this right now because I've not checked out these sources here at the moment, but it works. You can just use the Hugging Face tokenizer with this and have everything like you would in Python almost. Okay. With the added benefit that you also get the typing, and it's in Haskell. And going back to what I said at the very beginning of the meeting, I want to use that for program synthesis, right? So like where I want to fill holes in partial implementations of programs, and use like these big language models to rank different possibilities that you could come up with in an entirely symbolic way. And here I have almost all the pieces together to do that. I have a language where there's extremely strong support and tooling for symbolic reasoning, and especially for code, and many typing rules and type checker algorithms for different typing paradigms and theories have been implemented already. You can find tons of implementations from grad students around the world on GitHub. And
the nice thing is the GitHub semantic parsers, that's also in Haskell.
It is, yeah. Although this one is also just the wrapper around the tree sitter parser.
Okay. Yeah.
But yeah, they did a lot of extra work on top of it to enable the sort of semantic reasoning on top of the parse trees, that kind of tree sitter. But yeah, so like this just shows you that typically Haskell is the language people choose when they need to reason and manipulate code. Yeah. And I think enabling neural model approaches to this sort of manipulation is some of the strengths of what I'm doing here. Yeah. It's definitely a niche, right? So I'm not claiming like I want to compete with Hugging Face here on all fronts, but I think it's an enabler for people who wish that more of these like neural language model techniques would become available in a language like Haskell.
Yeah, I think you hit the nail on the head there. I mean, if you're trying to reason about code, you're going to have to re-implement the wheel, in some other framework here. So really, yeah, I think with a lot of language modeling stuff, it's kind of very sequence based. But if you're trying to fill a hole, say in a program, you'd really like a more semantic representation,
Mm-hmm.
and it seems like this has the right level of abstraction for doing that. I was wondering, maybe another digression. Maybe, I don't know if you care to comment, but a lot of times in natural language modeling, they're trying to do is kind of imitate or to do distribution matching, where you're trying to capture some other distribution in your data set. But here, it seems like for program synthesis, you also want to generate some new thing that doesn't exist in your distribution. Maybe it doesn't, in your data set. You want to reason about some new things you've never seen before. So how do you see the path towards kind of generating new knowledge, or proof kind of search using this type of kind of meta programming, or have you thought about that at all?
Yeah, I have thought about this a bit, but I think that's a longer horizon.
Yeah.
I think what you're getting at is sort of like the compositional generalization of or the lack thereof of contemporary neural approaches, right?
Mm-hmm.
So this is something that is subject to active research with very little progress so far. So maybe you are familiar with a Kaggle challenge that Francois Collet has put out about symbolic reasoning. So they're like little pictures, basically like IQ test sort of pictures.
Mm-hmm.
And they're like 3 input-output examples of how you can, or how you're supposed to denoise or reconstruct like a partially corrupted image.
Mm-hmm.
And as a human, it's obvious what to do. But we have also like billions of years of evolution behind us, and a visual cortex that has probably been engineered to addressing these sort of reasoning puzzles. But neural models, like even if you use like models that have been trained on like huge corpora of images like ImageNet or what have you, right? And you used autoencoders and you try to autoencode the problem away, right? Doesn't work at all. Like next to no accuracy, right? And it's really, really, really bad. And you can ask, why is that? Right? And why is the leader of that challenge somebody who has entirely based the solution on basically brute force search with no neural, no AI component whatsoever. So it's because we're not there yet, right? So like the models we have right now, the system 1 reasoners, they're not system 2.
Yeah, I kind of do this high level pattern completion. It seems like well, there's some similarities kind of to what you're trying to do in your programming, right? But it's hard to capture that, what the goal should be. And another kind of added problem I know in some languages is that there's like a ton of ways to write the same thing semantically. So you kind of have to have these invariances, or some way to reduce them into like a normal form that you can do search over. But that's very interesting. Yeah. So what's your next steps here on Hasktorch, Joe? What's left to do in kind of bringing this gradual type system into production, and how do you what would be something you'd be happy with? You see people are using gradual types in their day-to-day work, or do you see these ideas kind of trickling into Python?
Yeah, so this is interesting question. So like I'm pretty happy with how this project has evolved.
Mm-hmm.
When I actually implemented Beam Search here for T5, right? Here's the implementation, Beam Search. I was happy to have gradual types here. Here, you see it, unchecked size, unchecked size. It's, I mean, I could imagine this becoming one way of sort of moving forward here, like combining the best of both worlds, of typed and untyped, as you please, right?
Mm-hmm.
If you ask me, like, is this complete, or is this sort of just a proof of concept, and I'm going to leave it at this? I don't think so. I think I will continue doing this. I have some new ideas of how to improve the API, but it's also a little bit incomplete still. So like, for instance, you mentioned tensor indexing, right? So this hasn't been done yet. And maybe there's some interesting stuff waiting for us. Mm-hmm. Also, like I want to bring more to for this like language model integration here. So like, I'm an NLP researcher myself, so this is where I'm comfortable with. So I will push forward with this, so I can use maybe this stuff more in my actual work, not just my fun work. Mm-hmm. Yeah. So for instance, like Google Summer of Code, I mentioned this earlier. So like we have a few projects there, a few applicants who want to work with me on gradual typing, and I think with them we're going to look at a few of the open problems we have, and of course Hasktorch is open to collaboration, right? So like they have a Slack channel that is easy to get access to, and actually, I can bring up the slide and then maybe come to an end here. Let me just bring it up. All right, so like there's a website, it's called Hasktorch.org. There's a Github. So like all the code you've just seen is on GitHub as well, github.com /Hasktorch. And if you send an email to hasktorch@gmail.com, we will see it and then give you access to our Slack. No questions asked. And if you're welcome to check it out. If you're someone from machine learning interested in functional programming, maybe you have seen talks online, or maybe you have played with it like back in the day in grad school, and now you're doing Python only. You wonder what could have been or what could be if you use more of this stuff, or if you maybe in Haskell already, like if you work on Haskell code bases, but you're interested in neural networks, just get in touch. Just reach out to us, and maybe there's some project we can work on. We'll help you with your work.
Mm-hmm. Okay, great. Yeah, we'll put those links. Hopefully, we could get the well, I guess all of the materials when we're done here. But I'd like to give a very special thanks to Torsten for preparing this tutorial for our reading group today. This was very kind of you to do this on short notice, and I'm glad we got the chance to get this in before our summer break.
Oh, you're welcome.
So maybe if I had some questions from, I know I have some questions from the audience. I don't know if they're, but
I can stay on. I have a few more minutes, I think.
Oh, I know we've gone over a little bit. That's true too. Well, let's see. Okay. Well, I think you've been very generous with your time already, Torsten. Maybe I could ping you offline, because there's a bunch of things that I'd still like to ask, but
absolutely. You can just find me on Twitter or I think on the Mila Slack as well. Yeah.
yeah. Hopefully, I'll get a chance to drop in on your stream. That'll be great.
Okay. Cool. Thank you very much.
Take care. Thanks.
You too.